Hi guys, welcome back to the Tree of Math. Today we'll be covering volumes by rotation part 1. And today we'll be covering the disk and washer method. So the end goal of this video is to figure out why the formula for volume integral from bound 1 to bound 2 pi r squared of x dx, why this formula works to find the volume generated by rotation. So we have a very simple function here, y is equal to x squared, and previously in Calc 1, you guys learned how to find the area bounded by the curve between a function and the x-axis. So just as a quick review, the area would have been the integral from 0 to 2 of x squared dx. In essence, what you guys were really doing is you were finding out the infinitely small areas of the rectangles generated by the infinitely small widths dx and the certain height x squared for every rectangle. And you would sum that over all the rectangles in the interval from 0 to 2. So you took a one-dimensional height or one-dimensional value height of the rectangle, right? This is one-dimensional. You multiplied it with an infinitely small width of the rectangle, and this would give you area, which is a two-dimensional value. So one way to think about integrals is that you're essentially giving your integrand, x squared, you're doing something to it and increasing the dimension by 1. So that's one way to conceptualize one use of what an integral could do. So we'll take that same concept and apply it to volume now, right? So if we wanted to find volume, which is three-dimensional, so volume is three-dimensional, that means what we need is we need to integrate over some two-dimensional integrand multiplied by dx, which is our variable of integration. So let's say we wanted to rotate the shape bounded by x squared and x is equal to 2 around the x-axis. This rotation would give us some kind of pointy conical shape. Right, so this entire volume would be what we're trying to find. So just thinking about this 1 second, this dx still means the same thing as it did in area, right? It's just one slice, one particular infinitely small width of the shape. So if we just look at this cross-section here, what we have is we have maybe something like this, right? So we have this infinitely small width dx, and this would be the x-axis, and the height here would actually just be the value of our function. So this would be the height, or let's just say the radius as a function of x, right? So if this is one small slice of the entire shape, what we could do is we could just find the volume for this shape and integrate all the volumes that we would get from 0 to 2 for this particular shape, right? So volume of a cylinder would be pi r squared h, right? So the h is your dx. Radius, we already said, is your function, and pi is a constant, so we have everything we need. So just as a reminder, our integrand is a two-dimensional value. Pi r squared is the area of this circle right here. And then we're multiplying it with a very small width dx to get a very small slice of the shape. So this entire thing here would give you the volume of one small slice of the overall shape. And by integrating this very small volume over the entire bound, 0 to 2, or whatever bounds you have, then you would get the overall volume. So let's apply this concept to the problem that we currently have. The volume would be integral from 0 to 2, because those are our bounds, pi. Now the radius we just said is our function's value, right? Because at any point in this shape, our radius from the x-axis, or the radius from the axis of rotation, is given by the function y is equal to x squared. So at this point, let's say x is equal to 1.5, the radius would be given by y is equal to, or r is equal to 1.5 squared. So our radius is x squared, and then we square that again to find the area of the circle, right? So this would be our integrand, and then we multiply by dx for a small slice of the overall shape. So this would be pi integral from 0 to 2 of x to the 4th dx, and you can just use reverse power rule to get pi x to the 5th over 5, which is 32 over, evaluated from 0 to 2, which is 32 over 5 pi. So that would be the overall volume. Now, one question that arises is, what variable should you integrate with respect to? In this case, we integrated with respect to dx, because that is the axis that we rotated around. But in general, the direction you want to integrate with disk and washer is the direction that you want to integrate it. Right, so in this case, your direction was along the x-axis, and your axis of rotation is also along the x-axis, so you integrate with respect to x. So let's take a look at an example where we might want to integrate with respect to y. So let's take that same graph. Y is equal to x squared. This would be 2, so this value would be 2 squared, which is 4. And let's say we wanted to rotate this shape along the y-axis, right? So now our variable of integration would be y. But we need to reset the bounds, and we also need to reset the integrand to be functions of y. So we want to integrate from y is equal to 0, this line, to y is equal to 4, which is this line, right? So your direction of integration is along the y-axis, or the y variable. Integral from 0 to 4, pi. Now, previously we used x squared as our integrand, but because we're integrating with respect to y, we need to rewrite this function as, we need to redefine this function to be in terms of y, so x would be square root of y. So that would be our radius, and we need to square that because that is the formula for the disk and washer. So this would be our overall volume, and we can just resolve this integral easily with reverse power rule again. Integral from 0 to 4 of pi y dy, which would be pi y squared over 2, evaluated from 0 to 4, which is pi times 16 over 2 is 8. So you'd have 8 pi as your answer. And this shape would look a little something like a spinning top. Or maybe, I don't know, just a weird rock shape, I guess. But that would be the overall volume of that shape. This would be 4, 0, and x would be 2. So the reason this formula is called the disk and washer is because each cross-section of your overall shape is in the shape of a disk. Right, this is what we've been doing. In the case of Y, your disks would be horizontal. Or it's a washer, which is just a disk with a hole in it. So let's say you wanted to take the integral, or let's say you wanted to find out the volume of this shape bounded by y is equal to x and y is equal to x squared from 0 to 1 rotated about the x-axis. So in this case, each of your cross sections would have an outer radius, right, big R, and an inner radius, small r. So what you need to do is you need to find the area of this cross section, which would just be pi times your bigger radius squared minus your smaller radius squared, right? Just simple subtraction. So your overall volume would be integral from 0 to 1 of pi times your big radius, which is just x squared, minus your small radius, which is x squared dx. So this volume would be integral from 0 to 1 of pi times x squared minus x to the 4th dx. And again, using reverse power rule, you'd get x cubed over 3 minus x to the 5th over 5 evaluated from 0 to 1, which is pi times 1/3 minus 1/5, which would be equal to, what would that be? 2 over 15 pi. So that's an example of disk and washer where you just have a shape bounded by two different functions, right? So now each of your cross sections has a hole in the middle compared to just a solid cylinder. So that's the disk and washer method for volumes by rotation. And next time we'll be covering the shell method, which is a little bit different. So thanks for watching, and I'll see you guys next time.